All right. So we were looking at logistic regression, and we used a predict method and predict probability method. Now, how do you evaluate the model? How do you know whether the model is giving the right results or not? So for that, we have metrics for each and every model. For classification, metrics are different, and regression metrics are different. So are clustering metrics. Clustering metrics are also different. Okay, for metrics, if you check the metrics in scikit-learn, so there are so many of them. You have confusion matrix, you have distance metric, precision recall, okay, accuracy score adjusted. So basically a lot of them are the AUC, average precision score, Kalinski, Arabas, okay, Breyer score loss, and classification report, Cohen Kappa score, and then completeness score. See, a lot of them are there. Okay, you need not know everything, but at least you should know most of them if you want to be someone like SME or lead. Then you have to know most of them and where to apply each one of them. Okay, but we'll start with don't ignore this. I mean, this is not the right logic, but I was just trying to get everything that ends with score, thinking they are regression metrics, but then accuracy score is not regression metrics, so this logic is not correct. Okay, anyway, so these many metrics are there. Okay, out of that we have to choose the classification ones. Now for classification, interestingly, the most used ones are accuracy, confusion matrix, precision recall, F1 score, and then ignore the specificity. Then you have area under curve, receiver operating curve, okay, characteristic curve. So all these things are classification metrics. Now accuracy score is defined as number of correct predictions divided by total number of predictions. Let's just say 100 predictions you were supposed to make. Out of those 100, some were supposed to be no, some were supposed to be yes answers, but how many did you get correctly is the accuracy score. Basically, if you write an exam, and in the exam, what they calculate is the accuracy score. Let's just say you in your schools, your teachers corrected your papers. How many answers did you get correct? That was accuracy score. Okay, whatever the marks you got, that was accuracy score. Anyway, so accuracy score, we can calculate how many did the model get correctly. Okay, so accuracy score, if you do here, in this case 86.2% of the answers were obtained correctly by the model. Okay, so very straightforward. You are just trying to compare what was present in the Y test versus what was predicted, and that ratio is giving you 0.8620. Notice it is accuracy is not measured on the entire data set. In the entire data set you are not calculating, but instead the test data set that you had kept aside for evaluation, only on that you are calculating the accuracy score. Okay, now there is one problem with accuracy. See, accuracy usually works fine, but if the data was imbalanced, let's just say the Y test that you are comparing here with was imbalanced. Let's just say 80% of that Y, initial original Y had yes and 20% had no. Then generally, then when you split the data, most of the answers you originally got in Y test must be yes only. Okay, if they were yes, then whatever you have predicted against those yes, because most of them were yes in the training data set, model has understood the pattern as to be yes. So model now is kind of biased towards yes answers. So accuracy score, whatever the result it gives, will be inaccurate if the data set was imbalanced. So accuracy score we should not consider for imbalanced data set. It is applicable only for balanced data set. That is one of the limitations of accuracy. So that is explained here very clearly. So let's just say you are doing a problem where you are supposed to calculate cat versus no cat, whether the image that was given to you, whether the model has identified it as cat or not a cat. So in that scenario, if the data was 50-50% split, 50% of them were cat, 50% of them were non-cat, then the accuracy will make sense. But if there were too many cats and the model starts predicting everything to be cat, that happens usually in the ML world. So what will happen is accuracy will be inaccurate. So we can't consider accuracy. So that is just this one thing you have to remember. The next accuracy is, see, when you are using accuracy, let's just say you are working on a balanced data set, it is important to not only calculate the model accuracy, but also to calculate the training set accuracy versus trusting set accuracy. The reason is very simple. For training set, if you calculate the accuracy and you compare it with the test accuracy, then you would know whether the model is overfitting or not. Okay, if the training accuracy is very high, test accuracy is very low, then the model has learned the training data set extremely well that it is unable to identify test data set. That is what it means. So let's just say you have a kid, you only teach the kid to draw only cat, only the kid is drawing cat every day, and then you show a dog and ask the kid to draw dog, it won't draw, the kid won't draw dog, he or she will draw only cat only. Okay, because that's what he has practiced for over a very long period of time. So that is the same behavior in models also. So if you have lot of data which is very similar in training set, and the training set will be very high, if on the test data set your accuracy score is low, then understand the model is overfitting. If the model is overfitting, what is the solution? Very simple. Solution is regularization. Immediately you have to change your regularization parameter that we changed above. Yeah, L1 we changed, right? This lasso penalty, this is called as regularization. So penalty you have to bring, either L1 or L2 immediately, okay, on top of the actual modeling training process. That is one. Second thing is we have to tamper with this, tune, not tamper, rather tune the parameter C. Okay, so basically you have to test the model for various C values and see how the performance is improving. Now what we are trying to do is here, as you can see, because I have already used a L1 regularization, I already did. Okay, that's why I'm getting very close results. If they are very close, then understand your model is doing just fine. Okay, you don't have to worry. Let's just say I had used L2 regularization just for the sake of experimentation. We can do that anyway, it's not gonna take much time. I am gonna change the regularization here to L2. Okay, I will train it again, coefficients, intercept, predict. Okay, changed. Okay, now let's calculate the accuracy. Okay, it didn't change much. Okay, it didn't change much, which means we are good. Okay, now let's just say the results were different, very different. Then you can also experiment with L1 regularization. Why? It will get rid of some of the unimportant features. So you can also tune C value. C is the, so if you just run here, C usually is 1.0. One penalty. So is the regularization strength, how much regularization to be induced in the model. So higher the value, stronger the regularization. Okay, so this way you can experiment with various values here. Okay, now calculate the training and test score. It is getting trained. Okay, even now the scores didn't change. So which means the model was already doing good irrespective of c-value. C-value doesn't have much impact. So this is a good result actually. Okay, but otherwise, let's run another experiment where c-value is decreased. See, if you notice, the accuracy slightly decreased for c-value, lower c-value. That means c-value should be high for us. Okay, so that is the understanding here. So this way you can compare the accuracy. You can also calculate accuracy for something called null accuracy. Okay, so basically sometimes what happens is you can't tell properly whether the model is giving you the accuracy from the one different class or on the second class, I mean combination of both the class. So in order to understand that, what you can do is you can come up with null accuracy. Nothing but you can use only most frequent class that is available in the data set, and on top of that you can calculate the accuracy and compare. Then what will happen is you can immediately know whether the accuracy that the model was giving was coming from one class or the combination of both the classes. So here you have no as higher ratio, yes as higher ratio, lower ratio, and because of that null accuracy you can do the math. So very simple formula for accuracy, right? Number of predictions obtained divided by total number of actual rows. So this, if you calculate, it was 77.5, 77.6. Okay, roughly. Now what this means is, even though if we had used one single class, our accuracy would have, minimum accuracy would have been 77.6, but because the model has obtained additional 11 points, that means it is doing the classification on the both the classes. So that means our model is doing good job. Okay, our model is doing good job because we have done a lot of pre-processing steps. Okay, so that is another answer that you can give for accuracy score questions. Okay, so this is accuracy. You can, I have attached the link to this. This is a very good cohere.com website, has very good explanation for accuracy as well as many other metrics. I highly recommend that you take a look at it after the class. The next metric would be the one accuracy you got to know. So how many correct answers is the model giving, that you understood. But the second way of also looking at it is how just by, instead of saying how many correct answers you got, okay, now you are trying to calculate how many correct answers did it get which were supposed to be correct, which were anyway supposed to be correct answers. How many did it correctly predict those? The answers that were supposed to be incorrect, how many correctly did those predicted correctly, and how many correct answers the model has gotten wrong, and how many wrong answers the model has gotten as correct. So that variation also you're seeing. Basically, true positives means positive which the observations which are supposed to be correct anyway. For example, if the question was add two numbers 1 plus 1, okay, 1 plus 1 is 2. Now what we are saying is, this was the question, is how much, this was the question. Now we know the answer is 2. Answer is 2. Now what model has done is 1 plus 1 is, once it has predicted as 3, okay, once it has predicted as 2, okay, that anyway we are calculating. This will give you accuracy. How many times it has correctly predicted as 2 divided by total number of times it has predicted. This will give you accuracy. Okay. Now true positive, what we are saying is, let's modify the question a little bit. So let's just say, instead of saying 1 plus 1, let's just say A and B were there. A value was supposed to be 1 and B value was supposed to be 2. Now what we are saying is, how many times has the model identified A as 1? How many times the model has identified A as 2? How many times the model has identified B as 1? And how many times the model identified B as 2? This is what we are saying. So A how many times correctly predicted and B how many times correctly predicted. These will constitute true positive and true negative. Okay, if I say or if I say A and B as patients, this person has cancer. Okay, another person does not have cancer. Okay, no cancer. Now what we are saying is how many times the model has correctly predicted a person has cancer. Patient A has cancer. Okay, and patient patient B has no cancer. This is true positive is this, true negative is this. Correctly predicted. Basically, one patient has cancer, another patient doesn't have cancer. Both positive case, negative case, correctly identified. These are true positive and true negative. False positive means even though the person did not have even though the person had cancer, he was supposed to be positive. Okay, yeah, the person was supposed to be positive, but the model said he doesn't have cancer. Okay, so false positive means, no, false positive is for B. So false positive means cancer, false positive means no cancer. Okay, so a person did not have cancer. B, let's just say, did not have cancer, but the model said he has cancer, so it became false positive. Person had cancer, I will write it here. Person did not have cancer, but model said he has cancer. That is false positive. So if a model says false positive, that person will get checkup done again, because the model is saying he has cancer. He has to again go to the hospital, get himself checked. Okay, that is false positive. Okay, and false negative means the person okay, no cancer. False positive means, okay, see, person A had cancer, but the model is saying he doesn't have cancer. Okay, that means person had cancer, but model said he doesn't have cancer. That means this is called as false negative. Okay, that means this person will think that he doesn't have cancer and he'll stay at home. Then he will, because he already has cancer, that cancer will become from benign stage to, it will go to next stage, from malignant state to, I don't know the order actually, benign and malignant. Okay, anyway, so whatever the order, he'll go to serious stage and there is a chance of his death. So this is serious. This is very serious. Irrespective, in medical use case also, even in fraud detection also, if a person did the fraud, but the model said the person did not do the fraud, credit card fraud, that means company is going to end up losing the money, because model is saying he is innocent. Okay, even though he has done the fraud. So this case are usually severe cases. This you cannot have false negatives at any cost. Okay, again depends on some use cases. Okay, so depends on use case to use case basis, but usually it is recommended that you decrease the false negative. Okay, false negatives are the cases where we predict a observation does not belong to certain class, but actually it belongs to certain class. So hence we call it as type 2 error also. Okay, it's also called as type 2 error, and false positive is called as type 1 error. Okay, in a medical use case, remember this, in medical and fraud detection use cases, false negative should be lower as possible. Okay, in law enforcement use cases, false positives should be low. What is false positive? False positive means person did not have cancer, but the model said he has cancer. That is false positive. Now apply it to criminal case. Person did not commit theft or murder, but the model is saying he committed the murder. Okay, if the model said he committed the murder, he will be put in jail. Unfortunately, even though it was false positive case, the person will end up spoiling his entire life. So in law enforcement use cases, your type 1 error should be low as possible. Okay. In medical use cases or fraud detection use cases, your false negative should be low as possible. Okay. So these are some of the components of a confusion matrix. Now we have not yet even talked about confusion matrix. We are still discussing the components. So did you understand this? Did you understand this with this example? Okay, everybody. Okay, all right. So next, what confusion matrix does is, confusion matrix is just yet another detailed way of calculating the model results by making use of this 4 different components. Now again, there is another catch. When you are using confusion matrix, okay, so let's just say I'm gonna calculate the confusion matrix values here. You should know what is on the upper side and what is on the left side. Okay, I'll explain what I'm actually talking about. See, understand what is meant by actual and what is meant by predicted. Actual means what existed before in reality. Predicted means what the model is saying. Okay. Now, in this example, in the very same example, as you can see, true positives were in the total data 1,15,000 records. 11,000 records. 11,000 records. 8,000 records were true positives. Okay. And true negatives were 1,380. That means if you combine these positives, true positive and true negative, if you combine only the true cases, what existed, these are telling you that true positive means it rained, because we are talking about rain use case, right? Whether whether it has rained or not, that is what we are discussing. So 8,335 times it rained. Okay, 1,380 times it did not rain. Okay, these are true cases, actual cases. Okay, and false positive means 519 times the model said it is going to rain, but it did not rain. False negative means, okay, 1,050 times the model said it will not rain, yet it rained. Okay, that is what we are calculating. Now you have to get one thing correctly here. What is that? Your actuals versus predicted. Now how will you calculate these actuals versus predicted? Actual means you have to get this right. Okay, so actual means what the reality was and what the model is saying, both should be same. That is actual. Again, actual means what the model said as no and what the model said as no and in reality what was no. Now when you get these actuals versus predicted calculations correctly, okay, notice the okay, when you do the heat map here, okay, see, usually predicted values will be on the top. Okay, but in this case it all depends on how you are calculating this matrix, CM matrix. Okay, if you take the data, where is the data? So you have taken actuals first, Y test you have calculated first. Okay, let me calculate the same thing above, but by interchanging these. This is very important. Okay, otherwise you will never be able to explain these results to anybody. Notice the order. I just want you to understand the order. Actuals are along the diagonals from the left to right side. 8335 and 1380, 8335 1380, that will not change. So your actuals will not change. Okay, all right. So what I'm trying to do is, here I'm trying to reverse the order of calculation in confusion matrix and try to explain you how to get the predicted and actuals correctly. If you don't get, you won't be able to explain the results. Okay, are you able to see my screen now? Okay, okay, all right. So if you use y test first in the order, okay, your actual will be either on the bottom or on the top. That means your x-axis will be actual because you're using y test first. Y test on the first side, that's this will indicate x value, this will indicate y value, hence your x-axis will be actual and y value will be the predicted part if you use this. But if you use this, your predicted part would be on the x-axis and the actual will be on the y-axis. Then the answers will be flipped. This one 1050 and 519 would be flipped. So you have to be mindful of this. Okay. So here when I'm calculating, my x-axis is in the actual and y-axis is in the predicted. Now only basis on these actual versus predicted, I can calculate the false positives and false negatives. Okay. How is that? So true positives, that is false positives, we have formulae for each one of these. Okay, anyway, I will talk about this in the recall and precision part. But for now, just understand, get this right. If you are using y-axis, y-test first, make sure your actuals are on the x-axis. Okay, this is how you can calculate how many are obtained correctly versus how many you got obtained incorrectly. Now when you calculate this, always remember, okay, true positive is the first box, true negative is the second box along the diagonal. Always this is true positive and this is true negative. Okay, now false positive and false negative may flip. So if you're using y test first, okay, index, see the index, this is predicted, this is actual. So this actually negative, but the model said yes. Actually negative, the model said yes. Actually negative, the person did not have cancer, but the model said he has a cancer. So what is that? That is a false positive. So this is a false positive. Okay, false positive, and this is a false negative. Sometimes they may flip. Okay, next way of calculating the details is classification report. Now in classification report, highly depends on these confusion matrix values only. So if you notice, true positive, true negative, false positive, false negative, these are what are used in classification report. Now classification report, the moment you generate it, it generates various things, various couple of things. It generates what is the recall for each one of the classes and what is the F1 score of the class. Now recall, always remember, recall and precision, they are interdependent. Okay, what is precision? Precision is false positive measure, the false positive that we just discussed, this one, false positive type 1 error is being measured by precision. Now how do we, the easiest way to remember is FP, right? Precision, and then there is false negative, recall. So look at this P letter. So this way you remember, this is the easiest one. If someone is talking about false positive, immediately you should know they are talking about precision. This is one of the interview questions. Okay, this is also a question that I prefer to ask, and often students get confused. Okay, So false positive is measuring precision, false negative is measuring recall. Okay, so this way you understand. Now what we are saying here is false positive. That means out of 100% of the answers, 11% of the answers, that is 100 minus 89, 11% of the answers were obtained incorrectly by the model for no class, and remaining 27% of the answers were incorrectly obtained for yes class. That means the model said it won't rain, but it rained, okay, for 11% of the cases. The model said it will rain, but it didn't rain for 27% of the cases. Okay, that is what precision is saying. Likewise, recall. Now, recall is a measure of false negative. That means for 6% of the cases, model said it won't rain. Sorry, model said it will rain, but it didn't rain. Okay, it's the other way. Okay, and same holds true for yes cases. If you notice, generally for no cases the model is doing better. For yes cases the model is not doing as good as what it could do, and that you can also see in F1 score. F1 score is a combination of these two, harmonic mean of precision and recall. So your F1 score is saying 91% of the times the model is doing good job on no, 64% of the time it is not doing yes. This is a problem. The moment you see these F1 scores which are not correctly, it will also display you the how many values were there, okay, for each class. Immediately you should go back to the next experiment, as in you should retry the process again by doing a oversampling. So you should increase the number of no yes cases and then do the modeling, or you should decrease the number of no cases. But either way you have to modify your data again and redo the process. Even though your accuracy score is good, your confusion matrix scores are good, okay, but your F1 is saying that your model is not doing good job on yes cases. Hence you have to repeat the whole process again, whole model retraining part. You have to go back and add additional pre-processing step, wherein which you will oversample the number of yes cases and then come back, and then again repeat the same process and come back here until you get 90% here as well. Okay, so this way you have to understand the classification report. Recall and precision we'll talk in depth, but this is how you should read the classification report results. Accuracy you anyway you know, accuracy you already know, and accuracy, macro, average, weighted average, we'll talk about this. Okay, but so far I hope you have understood the false positives and confusion matrix, right? Can you give me a thumbs up if you have understood? Yeah, yes, Sachin. Mm-hmm. Mm-hmm. Yeah. Mm-hmm. Precision and recall. Mm-hmm. 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 Correct. Mm-hmm. Yes. Mm-hmm. Yes. Yes, I absolutely, absolutely, always. The answer is always. Um, Malakshmi, you can mute. Yeah. So yes, it's correct. See, it's depends on the use case and what the business is asking. Okay, for some of the cases that include, for especially for medical cases, um, as we have discussed, see, your false negative should be the important one. Recall should be the important one. Okay, precision is a good metric, but recall should be given more preference there, especially for medical and fraud detection. Okay, for law enforcement, precision should be given more important. Okay, so again depends on the use case. I was working on a use case uh, on order to cash and procure to pay life cycle, wherein which we were giving more preference to false positive, even though we were working on fraud detection. We were giving preference to false positive, but ideally we were supposed to give importance to false negative, again because the business asked for it. You- okay, but as a data scientist or as a someone, ml engineer, ml ops engineer, it's your job to convey that message that for false, I mean, certain metrics have to be given importance in certain use cases, right? For example, for medical, you always have to give importance to recall. Okay, that should be your first preference. Otherwise, what would happen is people who have cancer will end up dying, thinking they'll think they don't have cancer, but they have cancer. So this metric should be same. This applies to COVID also. You can apply to COVID if not cancer. Okay, sometimes the test, COVID test would come back negative, but the people have COVID. Okay, it's just that it's not grown so much. The viruses have not grown so much inside your body. So in that case, the person, there is a risk now. There is a risk is the person might end up dying if you don't. Um, if the model says there is it's negative, but you have to give importance to this one. That's why it's very important. Okay, life saving metric. Same holds true for fraud detection. If you say the person is innocent, the company will end up losing money. See, it is okay for a person to not have committed the mistake and taken for investigation and let them go. Later, after investigation, they'll find him innocent, they'll let him go. Small inconvenience caused, but no loss of dollars. Okay, but for recall, the company will lose money. So recall should be given more preference there. But for law enforcement use cases where you are trying to identify, even in image detection problems, right? If you're trying to identify someone as a criminal or someone who has done some uh, breached certain things, it's a serious metric. Precision takes over now. Now recall is not important. Precision is more important. Otherwise, you will end up jailing a person who has not committed any crime. Okay. So this way you have to identify the metrics and use it, and that is what precision and recall are talking about. So moving on. So precision is nothing but the percentage of correctly predicted positive cases. Okay, it's a measure of both positive cases, true positive and false positives. So if the model correctly identifies a criminal as criminal, a innocent person as innocent person, then it's a precision, and that is what you should get it right. Okay, for criminal cases. For other cases, Okay, for that what we discussed above. So precision may not be that important. So precision is a measure of false positive, because in denominator you have false positive. True positive divided by true positive plus false positive. Okay, so if you make this false positive 0, then your precision becomes 100%. Okay, if let's just say true positive was 5, again same true positive you are taking here, 5 divided by 5 plus 0 is 100%. So you can improve the precision by decreasing the false positives. Closer the false positive to 0, lower the denominator, hence higher the precision. Okay, so this I'll write it down here. Lower the false positive, okay, lower the false positive, higher the precision. Okay, so you can just make it should be closer to 0. If it's high, false positive is, let's just say 100 here, and this is 5, true positive is 5. 5 divided by 5 plus 100 is 105. True positive, I mean the whole value will be very low, precision will be low. So that way you can understand. So always you have to decrease the false positives. And recall, on the other hand, is a measure of false negative, nothing but correctly predicted positive outcomes out of actual positive outcomes. Okay, so now you are only talking about the positive outcomes, but how many were there? Out of that, how many you got it correct? For example, multiple choice questions were given to you. Out of 100 questions, 50 were supposed to be 50 of them had correct answer and 50 of them did not have correct answer. It is important for you to also check the incorrect answer for an incorrect question. If you check something else, then you won't get that scoring. Okay, so that is what recall is measuring, correctly predicted positive outcomes out of actual positive outcomes. Okay, so as you can see, in the denominator you have false negative. Okay, lower the false negatives, higher the recall. Same thing here also, lower the false negative, higher the recall. But here's the catch. Okay, there is a dependency between recall and precision. What is the dependency? The dependency is FP and FN. Okay, so it is in a real world scenario, it is really not possible to decrease both FP and FN. That means if you are going back to the same example above, easy to explain here. So false positive is this: if you are saying that the person did not have cancer, okay, he did not have cancer, but if you are saying he has a cancer, that also means that the person who had a cancer, sometimes you okay, how do I put it in simple terms? Let's just say, out of these two patients, one patient you are saying person doesn't have cancer. Okay, here you are saying, model is saying person doesn't have cancer for one person. Let's just say that patient is A. In reality he has cancer, but model is saying he doesn't have cancer. Okay, what that does, what it means is, for one patient if you are saying he doesn't have cancer, okay, that means out of two patients, one person you have already said he doesn't have cancer, but the other patient, I mean, if you combine both the patients for calculation, 50% of your calculation is already incorrect. Do you agree? If two patients are there, for one patient you are saying he doesn't have cancer, but he actually has cancer, okay, 50% of that calculation is already gone. Now for the second measurement, okay, in the first measurement false negative took a hit, recall took a hit, but because you are going to use patient A for the second calculation, also for the calculation of precision, also you are taking A, for the calculation of false negative, that is recall, also you are taking A. But you already got calculation of patient A incorrectly once in the very first attempt for recall. That means you have already determined one calculation incorrectly, which will also be taken into account for the calculation of precision. That's why they are dependent. For the second patient, you are gonna say, let's just say for the second patient, no cancer. Let's just say you say he has a cancer. Okay, this became false positive. But what about the first person? For first person also, you already made the calculation. You already determined that he doesn't have cancer, which is also incorrect, right? That means in the first case, false negative took a hit, which also is dependent on false positive calculations. Okay, because you are essentially using the same rows of data for both false negative and false positive. Hence, we say it is inherently not possible to reduce both. If you reduce both, that means you are doing exceptionally well. Your model is well suited for the problem. That is what it means. Okay, but there is a dependency. We call it bias variance trade-off. Okay, so one second. Recall, precision, there is no graph. Here also there is no graph. One second, there should be some image. This one. Okay, see, you have error rate, which is this. So see, precision is what it is calculating is bias. Okay, and variance is being calculated by recall. So variance curve is different from precision curve. This again I will show you in depth and explain how they work. But what I am trying to say is, if you decrease one at this point, notice recall has already increased at this point. If you decrease recall at this point, precision error is high. So you can only strike a balance between those two and reach this point where both of them are low. Okay, so this way both bias and variance errors can be low. Total error will be low only if you hit a balance, because both are dependent on one another. Okay, I'll explain you this in depth. But for now, just understand there is no way to reduce both recall and precision perfectly to very minimum. Both can't be 99%. Okay. The next metric is, have you understood recall and precision, what we are talking about? And recall is also called as sensitivity, and precision is called as specificity. Those are just terms, statistical terms. Don't worry, both mean one and the same. Next is true positive rate. Now in true positive rate, notice this is exactly the formula of recall. True positive rate is nothing but recall. False positive rate is nothing but, false positive rate is little different. Just compare the formula. False positive rate is talking about false positives, but for formula for precision is different. Precision is TP divided by TP plus FP, which is different from what you see here. So true positive rate means recall. Okay, which is what we have obtained. False positive rate means basically what you are saying is the false positives that we have calculated. Okay, how are they actually, are they coming out of the negative cases, true negative cases that we have? So basically all the patients that did not have cancer, we have taken those patients. Are we seeing any false positives from them? Okay, generally false positive should be measured in true positive, but what we are trying to determine here is from the patients who did not already have cancer, are we seeing a trend? Is the model making misclassification in those patients only? That is what false positive rate is measuring. Now, false positive rate and true positive rate. So essentially, as you can see, 27% of the time the model is thinking people who don't have cancer, okay, there it is making mistake and thinking them as cancerous, okay. So that this calculation is done. Next is specificity. Specificity is precision. Is the no, specificity is also slightly different, okay. So we have to take true positive for precision, but here we are taking true negative. Now, out of the, I think false positive rate and specificity both are measuring the true negative cases. If you can see, true negative as well as more preference is given to true negative cases. That means people who are safe. So there we are calculating. So specificity is 72%. If you add up these two, specificity and false positive rate, I think you will get 100%. Yeah, you will get 100%. So basically false positive rate is saying, okay, first understand what is false positive. False positive means person who had cancer, okay, is true positive. Person, if a person had cancer, that is true positive. False positive means person did not have, person had cancer, we said he doesn't have cancer, okay. No, it's the other way. So person did not have cancer, we said person has cancer, okay. Person did not have cancer, but we said person has cancer. False positive. So positive means has cancer. False means we are saying he has cancer, but he doesn't have cancer. That is what false means, okay. So that is what false positive rate is measuring. But specificity is talking more on the safe candidates who already don't have cancer, okay. So this way you have to get these things right. It's I know it's even confusing even for the seasoned data scientists sometimes, but it's okay if you get confused. You take your time and figure these things out. So all these are metrics you have to explain to business how your model is improving, how your model is making decisions and all of that, okay, how well your model is performing. Now F1 score is a mean of precision and recall, harmonic mean. That means you take the addition divided by product, okay. Harmonic means you add them and then divide them by multiplication of them. So that is harmonic mean. Now F1 score will immediately tell how well your precision and recall are doing. Higher the F1 score, better your precision and recall will be, okay. So instead of measuring precision and recall as a separate metrics, you can measure F1 score instead, okay. Now support is just a way of combining all these metrics. Classification report, if you see, let's calculate and then understand, okay, this is different. So you have support as well, okay, in the above classification report. Support, okay, support is telling you how many cases were there, for that how many cases were taken into account for that measurement. That is what support is, okay. Next is, after you evaluated all these metrics, the next step for you is how to adjust the threshold, okay. Now you can see from the results you have true, these are correctly predicted along this left to right diagonal, and right to left diagonal they are incorrectly predicted. How to decrease this is the question now, okay. And how to tune, if you increase one, the other can be decreased, the other, if the other has to be decreased, the other has to be increased. So that way, how do you tune, how do you decide which one to keep, which one to increase and which one to decrease? That is the question. That you can do by tuning adjusting the threshold level. By default the threshold level is 50%, okay, but you can change that threshold. So let's do the actual calculation. So these are the probabilities that the model has already generated for 50% case. Um, 1 second. Where are the okay. Where is the threshold increased? I'm just trying to understand where is that threshold given while doing the prediction. 0.1. Okay, here. So so what we are doing is we are going to consider various threshold levels. I value is used between 1 and 10. Okay, that means 9 different use cases are used starting with 1. Okay, and if you divide one value by 10, what will you get? 0.1. So that means 10% of the threshold. So for various threshold levels, we are going to print the matrices results. When the threshold value is 0.1, notice the results. False positives have increased, false negatives have decreased, but that was not the case before. So this is how you will tune it. If your use case demands that you decrease the false negatives, these are false positives above. If you want to decrease the false positives and increase the false negatives, for example, this use case, false positives have to be lower. Okay, law enforcement use case. Then you have to decrease the threshold. If you want to improve recall, then you have to increase the threshold. Okay, so this also means for loan approval use case, if you say 50% is the threshold, that means anybody who is getting 50% as the probability will get the loan. But if you want to decrease the number of people getting the loan, only the ones who have all the features properly set, if they are the ones who are going to get the loan, then you have to increase the threshold. That means your false negatives will decrease. Okay, that is what we are trying to see. What we are trying to measure is, if we set the threshold as 0.1, then you can see you are increasing the false positives, false negatives are decreased. Okay, so notice the accuracy has also taken a hit. Sensitivity, specificity, so those are changed. And notice for 0.2 threshold, these things are decreasing. Compare this with above one. False negatives are increasing now, false positives are decreasing. Okay, so basis on these threshold use cases, you have to set the thresholds. So here 0.3 threshold means false negatives have increased, false positives are again improving. Okay, this way you can continue till certain threshold. The moment you reach the 0.9 threshold, your false positives have decreased. Okay, there are only 12 false positives, but there are 2000 false negatives. The business can overlook this. For example, false law enforcement use cases, you have to set the threshold as very, very high, which means you are going to say 12 out of let's just say 11,000 people, or whatever the number of rows are, out of 11,000 or maybe 15,000 people, only 12 have been incorrectly punished by the law. Okay, only 12 people who are innocent have been identified by law as criminals, but rest of them, see, 8,842 and 322 were correctly identified by the model. That means 322 people who are not criminals have been identified as not criminals. 8,800 42 people who are criminals have been identified as criminals. Only 12 people who are not criminals were identified as criminals. I hope I'm not confusing you by repeating very similar sentences. Are you getting confused or are you following me? You're following? Okay, very good. Okay, and 2108 people um, who are not criminals actually. Who are not criminals? Sorry, who are criminals? Actually, 2108 people who were criminals were identified as not criminals and they were let go. And that is what our Indian constitution also says, right? It is okay to let go of a criminal, but we should not punish the innocent man. That is what our inherent thing. You can look it up about the constitution thing, but that is what the law practices, belief system is in the law enforcement. So that's why false positives have to be reduced. It's okay for 2000 criminals to roam free. That is okay, but we should not punish the innocent. That is what we are talking about here. 12 people were innocent, but we said they are criminals, and that is why our threshold should be very high to reduce these false positives. Okay, but now apply the same rule for cancer patients. Now everything changes. Now again you have to set your threshold to lower. Okay, here what we are saying is it is okay for 3226 patients who don't have cancer, and we say they have cancer, they come to hospital, get it checked, and they go back home safely. No harm done there. It is okay for this number to be high. Okay, but we cannot have this number to be high, 151. We cannot let people who have cancer be identified as not having cancer and let them die. So we can't do that. Okay, so that's why our threshold should be lower for such use cases. So accordingly you can judge. Okay, you have to make that call. This completes your evaluation metrics. But yeah, there is one more I want to talk about, very very important, and this is where most of the people also make mistake. The next one is ROC AUC curve. First understand what they are talking about. See, this is a very good link from Cohere. I recommend you go through it, and most importantly you go through the section where AUC ROC curve is talked about. I think, is it here? Yeah, so it is here. See, the false positive rate that we talked about, notice this. What model is doing is it is measuring true positive case versus false positive rate. That is how model is able to identify all the true positive cases correctly and false positive cases correctly. So we want model 3. Model 3 is the best performing here. It is correctly predicting along the training level. If this curve was below this dotted line, then the model would have been terrible. We can't have such models. So same thing is here. Now for this same for the same true positive versus false positive cases, what we are gonna do is we are gonna measure area under curve. So basically we are going to use integration and calculate the entire area covered by this curve in the square. Okay, so higher for model 3 the area under the curve is very high. That means it has correctly identified true positive cases versus false positive cases. Hence we want model number 3. We will discard model number 1. And if these lines were below this, area under the curve would have been even lower than 0.5, and we don't want that model. So generally anything above 0.5 is desired. Okay, actually desired is 0.9 and above, but recommended one is more than 0.5. Okay, that's why when you measure your true positive case versus false positive case, area under curve will be higher. If it is higher, it means the model is able to separately identify good cases, positive cases versus negative cases very well. It is able to segregate the decision boundary. It is drawing to separate those points is very good. Okay, and 75% is also, I mean, it is decent enough. Okay, but 90% and above is recommended, but 75% is also okay. If it is 50%, that means model is not able to identify positive case from negative case. If it is 0%, it's problematic. The model is pathetic. You just have to throw it in garbage. So that's what it means. Okay, the model is not at all working. 0% means. Okay, so this way, area under curve, what it is doing is, it is talking about how well the model is able to separately identify positive cases from negative cases. Maybe. Okay, this way. For us, the curve is like this, and if you calculate the values here, we already have there is AUC score. I think we have not called AUC score. Anyway, okay, here it is. AUC score is called here. So as you can see, I'm so sorry guys, my pointer is not working correctly. Okay, AUC score is 89.43, which is very good, close to 90%. Okay, AUC curve, you should understand that it is talking about the false positive rate versus true positive rate. The curve that is drawn by ROC, which is true positive versus false positive, that area is being measured here. And if the area is more than 0.5, your model is doing good job. And desired is 0.9. Okay, this is yet another metric where you can use. Okay, next step is, after measuring all this, you can do one more thing. Remember, while doing the training, we randomly selected the rows and columns, hence we had set random state equals to 1. You can do one more thing. What if you could use every single row for both training and validation? That is possible, and that is possible by making use of this cross validation score. What you are going to do is, you are going to pass the model, you are going to pass the data, and for every 5 rows we are going to say do 5 runs in such a way that for every 5 rows, pick 5 rows randomly. Out of 5 rows, use 4 as training data, 1 as validation set, and calculate the accuracy. Okay, this is very important. So most of the time you can improve your model by doing the cross validation. And when you do, okay, see, for 5 different runs, it has calculated the scores and taken the average. Average cross validation score is 0.855. Original was 0.847. So it has improved the model by little bit. Okay. And one last topic is hyperparameter tuning. Now for hyperparameter tuning, we have 4 different options or 3 different options: grid search CV, random search CV, and Bayesian optimization. I will explain Bayesian optimization in depth in Bayesian regression, but for now, grid search CV and random search CV. Grid search CV means all the values that you have taken will be cross matched. This one and this one will be considered in the first run, this one and this one will be considered in the second run, this one and this one will in the third run, this one and this one in the fourth run. The same will be repeated for this one, the L2 one. So how many are there? 2 into 4 is 8. 8 different runs. For 8 different runs, the model will start picking whichever is the performing is as the best one. It is going to take time, by the way. So, and accordingly it will calculate calculate the scores and give you the scores, which model is performing. I think I have already run and I have obtained from 0.8501 I have obtained to 7. Okay, after this. So this is how you use the logistic regression model. Any doubts so far? Is this interesting, not finding interesting, complex, easy? You can tell me. Okay. Okay. Finally, with the grid search CV, we have found out the best parameters, and they are, we have to supposed to use C is equal to 1000. Solver we have to use liblinear, and random state 1 we can use. Okay. So first experiment you did, first experiment you ran all this code. Second experiment what change did you make? You made the data balanced and then reran. In the third experiment, what you're doing is you're gonna retrain the model using C equals to 1000 and re-get the results. So this is what the typical job of data scientist is: tuning the model, getting the best performing model, okay, and doing feature engineering and all of that. So multiple times you will do this model training part until you get the best performing model. You can no longer further improve the model. Typical job of data scientist. Okay, I will stop the recording here.